Thanks for coming. Albert Einstein sends his apologies. He wanted to watch the Blue Jay match tonight, so he's tied up. So he left it up to us in a series of meetings actually to explain what he thinks or what he thought about various important issues. We started last week with Chris Mink, who gave a talk about general theory of relativity. It's me now, engaging philosophy, Einstein on the method of science. Next week, not far from here, Doreen Fraser from Waterloo on quantum mechanics. And it's not last, actually, October the 28th, 2 weeks from now, Wayne Myhrvold, who's here in the audience, on the atomic theory. And then Chris Mink again on November the 10th, Einstein's universe. And finally, there's going to be this most likely to be very splendid exhibition of Einstein's papers and writings in Satellite Gallery for 2 or so weeks in November and December. So make sure that you attend most of these events, if not all of them. It's going to be like attending a short course on Einstein. And I'm sure the quality of the talks will be very good. Perhaps not mine, but you'll judge. Anyway, so tonight I'm going to talk about something that it's the converse of the motto of Rotman Institute, who is hosting the whole event, engaging science, the Rotman Institute says. It's engaging philosophy, a scientist engaging philosophy, Einstein on the method of science. And I'm going to start with a problem which is a fundamental philosophical problem which goes back to Aristotle. Throughout his scientific career, Albert Einstein was sensitive to a key philosophical problem that arises in our attempt to understand how science works and how in particular it manages to reveal us the structure of the world. This problem was first identified by Aristotle in an important, a famous, a significant book, Posterior Analytics, 3rd century before Common Era, and it occupied the minds of most philosophers and philosophically minded scientists throughout the centuries. I call it the problem of the first principles in science. Let me tell you that all the players that you're going to see in this lecture were famous enough to become stumps. Only one was not, unfortunately. You'll see a key player who didn't become a stump, and it's a big shame. But that's Aristotle, and roughly put, the problem is this. Science starts with first principles, which we know, from which we derive less fundamental principles, theorems or empirical laws or whatever. And this process is very nicely understood. It's deduction. We derive logically the theorems or the less fundamental principles from the axioms, from the first principles, not quite the axioms. But how do we arrive at the first principles themselves? Now, we cannot prove them by means of other first principles because we're going to have a regress. So it's not deduction that will lead to them. Aristotle thought it's not in our mind. They're not a priori independent of experience in our mind. Therefore, it must be experience that takes us to the first principles. And actually, he called this process for the first time induction, in Greek epagogy, the way by means we start from experience, and with a process he never actually described thoroughly, we arrive at the principles from which we start all demonstration in science. Now, a corollary of this, which was very important to Einstein, was what is the contribution of experience and what of reason in our scientific image of the world. If the ultimate test of a theory is concordance with experience, does it follow that theories are or should be dictated by experience? What's the contribution of reason? What's the contribution of experience? Now, Einstein was always very philosophically active. Even in his most technical scientific papers, he was making important philosophical points and philosophical ideas in operation. But was that idiosyncratic of Einstein's own personality? Shouldn't philosophy be left to philosophers? Are scientists entitled to do philosophy? Now, that's a long quotation is going to follow, but it's a marvelous quotation, how Einstein characterized the relation between scientists and philosophy. It has often been said, and certainly not without justification, that the man of science, the woman of science too, of course, is a poor philosopher. Why then should it not be the right thing for the physicist to let the philosopher do the philosophizing? Such might indeed be the right thing at a time when the physicist believes he has at his disposal a rigid system of fundamental concepts and fundamental laws which are so well established that waves of doubt cannot reach them. But it cannot be right at a time when the very foundations of physics itself have become problematic as they are now. That's written in 1936, quite a bit late anyway in Einstein's career. At a time like the present, when experience forces us to seek a newer and more solid foundation, the physicist cannot simply surrender to the philosopher the critical contemplation of the theoretical foundations. For he himself knows best and feels more surely where the shoe pinches. In looking for a new foundation, he must try to make clear in his own mind just how far the concepts he uses are justified and are necessities. So I take it that Einstein says philosophy has two kinds of roles or tasks vis-a-vis science. I call the first normal philosophical activity. And it's basically to clarify the conceptual framework that scientific theories use to represent the world. It's an activity which is really in force when there is a certain scientific conceptual framework in place. I take an exemplary of this kind of activity to be Kant's work on Newton. How Kant tried to clarify the conceptual foundations of Newtonian mechanics. What should the world be like in order for it to be knowable, in order for Newtonian theory to be true? But there is something which I call critical philosophical activity, and it's to create or contribute to the creation of the very conceptual framework through which scientific theories represent the world. Now, this normally happens when we're in the midst of a scientific revolution. Now, for Einstein, and I think that's a very good insight, the second philosophical task requires the engagement of scientists with philosophy. I call that critical philosophical activity because there is an element of critique of science and an element of crisis of science. So it's critical in this dual sense. Now, let's go back to the end of the 19th century, beginning of the 20th, and look at this period, a very fertile period where science was in deep crisis, and scientists themselves, with very few exceptions, were actually very much engaged in philosophy, aiming to secure the conceptual foundations of the new theories. Now, during this period, end of 19th century, beginning of the 20th, issues concerning the method of science became very prominent. Why was this period very special? Because all issues that we care about when we care about science were up for grabs, were being discussed. Geometry and the structure of space, the atomic theory of matter, the electromagnetic view of the world, Newtonian mechanics and its role in science, and ultimately the structure of matter and energy, which led to the emergence of quantum mechanics. I'm going to talk mostly about the first four, more detailed about that, in less detail about the other three. So these are the stamps. These are quite rare stamps, actually. I wish I had them, but these are the three key players in geometry until the end of the 19th century. Euclid, the geometry we all care about, the geometry we learn at our mother's knee, but in the end of the 19th century, non-Euclidean geometries emerged. Lobachevsky, Nikolai Lobachevsky, a Russian mathematician, and Bernard Riemann, a German mathematician, developed consistent mathematical systems which represent physical space, broadly speaking, in non-Euclidean terms. These are consistent mathematical theories, but then can possibly describe physical space. They make conflicting claims. For instance, in Euclidean geometry, basically, you've got a point outside a line. You can draw just one parallel to it. In Riemannian geometry, there are no parallels from a point outside a line, and in Lobachevskian geometry, hyperbolic geometry, infinite parallels can be drawn from a point outside a line. So there is a conflict, but it's a mathematical conflict. One might think, why should we care about physics? There were two influential responses back then, one by a German, very famous German physicist and mathematician, Hermann von Helmholtz, who said roughly that the axioms of Euclidean geometry, of any geometry, are empirical generalizations. We can prove them on the basis of experience. Now, a very famous French mathematician and physicist, Henri Poincaré, back in the 1890-something, said this cannot possibly be right. The axioms of Euclidean geometry do not refer to things we encounter in the space. They talk about lines, planes, points. No one has seen a point. No one has seen a straight line, strictly speaking. These are ideal entities which the mind somehow constructs or abstracts out of empirical situations like the movement of solid bodies. But if that's a situation, what are the axioms of geometry? Now, Poincaré famously said they are conventions. They are neither a priori true. Why? Because we can conceive of alternative geometries like the Riemannian and the Lobachevskian, but nor are they empirical generalizations for the reasons that we cannot encounter geometrical objects in experience on the basis of which we make generalizations. Do they characterize physical space in some sense? Now, here is a famous thought experiment Poincaré performed. Imagine we're on a disk. That's a world. It's a flat disk. It's a Euclidean disk, two-dimensional disk, and little people live on this, two-dimensional. They cannot escape from this disk. They've developed their rational faculties in such a way that they can think about geometry. So they try to understand what the geometry of the world they live in is. We know it's a Euclidean geometry. It's a bounded circle, a flat two-dimensional circle. But how would they proceed? They say, we're going to make measurements. And one measurement they can make is to see whether from a point outside the line, they can draw none, one, or many parallel lines. So they start doing an expedition. Many scientists go to this point and they start moving about. And how can we tell operationally when two lines are parallel? No matter how long we extend them, they never meet. So they start doing this physical experiment, but without knowing there is a very strange physical force in this world. A physical force which somehow heats up the world in such a way that things shrink as they move away from the center of the world towards the periphery. But because there is ideal thermal conductivity, no one understands how things actually shrink. Everybody shrinks as they move outside the circle, away from the circle and towards the periphery. But what does that mean? They're going to never reach the end. It's like the Zeno paradox. And besides, no matter how far they try, they're never going to make lines like that cross the diameter. So they come to a convention after a few months and they say, we discovered that the world we live in is Lobachevskian. It's an infinite world, it's an unbounded world, and it's such that from a point outside the line, an infinite number of lines can be drawn. And then a young mathematician shows up, I call him Lopernicus, and he says, no, there is an equivalent hypothesis here, namely, the world we live in is Euclidean, but nonetheless there is this strange force, this heat field, which makes everything shrink as we move outside the center towards the periphery of the world. So the community goes into crisis because you've got two hypotheses. One is that the world is Euclidean and there is this strange physics. The other is that the world is Lobachevskian, but the physics is normal. How do they decide between them? What Poincaré says, and I think he's quite right about that, we always test geometry together with physics. But he draws a conclusion that Einstein doesn't like at all. The conclusion is, therefore, we can always hold on to geometry by changing physics accordingly. So he says, Euclidean geometry has nothing to fear from fresh experiments. Why? No matter what happens, we can always think of the geometry of the world as being Euclidean and change or modify our physics. Now, that's a key disagreement between Poincaré and Einstein. Now, Chris spoke last week, and he said something really extremely important, namely, Einstein's theory of general relativity implies that space is not actually flat. Not only is it not flat, it's curved, but its curvature is variable. The curvature of the space varies according to the distribution of mass. So not only is it not Euclidean geometry, the physical geometry of the space, but not even any kind of non-Euclidean geometry with constant curvature. But making this big move to the claim that the geometry of the world is not Euclidean required an important philosophical shift. For Poincaré, the principles, for Einstein, the principles of geometry are not conventions. He wrote a wonderful piece, a must-read, Geometry and Experience, 1921, and he argued there that although we can always test geometry in conjunction with physics, we test this thing holistically, which means that we can either change the geometry or the physics. Geometry is not sacrosanct. We can always change the geometry and retain the physics. Hence, if there is conflict between geometry and physics, it is geometry that may be abandoned or modified if this gives you a simplest account of the world. So he said famously, according to the view advocated here, that is in this piece, the question whether this continuum, spatio-temporal continuum, has a Euclidean, Riemannian, or any other structure is a question of physics proper, which must be answered by experience and not a question of a convention to be chosen on grounds of mere expediency. Second big thing, the structure of the atomic theory of matter. Until the 1910 or so, the atomic theory of matter was a minority view among most scientists. It was mostly the work of this guy over there, a French physicist, Jean Perrin, who got the Nobel Prize in 1921, who actually showed that we've got good reasons to believe that there are atoms. And one way to do that, that is, there are molecules, that is, the matter is granular, it's not continuous, was the so-called Brownian motions. So you drop various relatively big particles like pollen particles or particles made by mastic or gumboats into a liquid, and then you see under the microscope, of course you don't see the molecules over here, but you see them, they're big enough to be seen under the microscope, you see this haphazard motion that they follow. And an explanation for this is that they hit on the atoms and the molecules of the liquid, and this explains why they've got this totally erratic haphazard motion. This was a well-known phenomenon called Brownian motion because of Robert Brown, a botanist, early 19th century, identified it as a special phenomenon. And the explanation was that it's because of the atoms that we find this strange behavior of these Brownian particles. Einstein wrote an important paper back in 1905, actually a series of papers defending atomism and explaining the atomic theory of matter and the atomic explanation of the Brownian motion. And all this was very nicely confirmed by experimental work and theoretical work that this guy, Jean Perrin, did in 1908, 1910. And all of a sudden, the scientific community shifted towards accepting the atomic theory of matter. I'm just scratching the surface. Wayne is going to talk about that in 2 weeks' time in great detail. But it's not just that. Electromagnetism. Einstein said Maxwell's theory of the electromagnetic field represents probably the most profound transformation of the foundations of physics since Newton's time. That's 1870, 1875, 1818, 1880. But as Chris Smink said last week, there is a very strange thing here. The speed of light. The speed of light is constant. Everybody knew that. But it's not just constant, it's independent of the motion of the source. So that's a very strange property of the speed of light. And this meant something really important, that Maxwell's equations, fundamental equations of how electricity and magnetism work, violated the fundamental principle of physics. They were not invariant under Galilean transformations. Now, what are they? Very, very briefly, again, Chris spoke about that. Galileo, another famous guy, and he became a stump, actually far too many stumps. He said somehow that the state of motion, if it's kind of if it's inertial motion, that is, if there is no acceleration, the state of motion of an observer or a frame of reference should not be such that the laws of nature change according to the motion. So whether you move or not, insofar as your motion is with constant velocity, a rectilinear constant velocity, then there shouldn't be any difference in the way you perceive the laws of nature. The same equation should hold. And these are the famous transformations. I don't think they are Galileo's, but they were already known when Newton wrote the Principia. And it's basically the way we think about how motion relates to our experience in our everyday life. But it's really important, but this kind of transformations were violated by Maxwell's equations. And an important Dutch physicist, Hendrik Lorentz, devised a new set of transformations which live invariant Maxwell's equations, but lo and behold, in this transformation, something really strange happened. Time also changes. Time is not constant between the frames of reference. It's not the same. We've got to transform the time as well. So there is a dilemma back then. Either the Galilean principle of relativity has to be abandoned or it has to be transformed. Now, Einstein, very early on, 1905, the miracle year of the special theory of relativity, suggested that we should transform the principle of relativity. We should actually adopt Lorentzi's transformations as the transformations which connect inertial frames, and thereby make sure that Maxwell's laws hold in all inertial frames. But to do that, we had to change our concepts of space and time. Actually, as he says here, this is the idea that the invariance actually is in all physical systems which express general laws with respect to Lorentz transformations, not to Einstein's, not to Galileo's, is the key element of the special theory of relativity. But as I just said, to do that, we had to reconceptualize our notions of space and time. So we no longer have absolute simultaneity. We can no longer say these two events happened at the same time. It all depends on the motion of the observer who actually makes the measurement. And the same goes for space. And of course, this is a famous diagram which goes back to another important German mathematician, Hermann Minkowski. That's not Einstein. How now you've got, instead of space and time, space-time with a complicated structure which is clearly distinct from the Newtonian structure of absolute space and absolute time. Finally, Newtonian mechanics. Everybody back then was thinking that that's a global theory, that everybody should actually adopt this theory and should be the foundation of all processes. All processes in nature should be reducible to, to Newton's laws. And actually, there's a famous second law. That's a French stamp for Newton, and that's a bit ugly for obvious reasons. Now, the second law says the change of motion is proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. Everybody knows that. F equals ma in modern terms. And then what turned out to be the case is that instead of actually reducing electromagnetism to mechanics, we had to modify, and Einstein preferred to modify the laws of mechanics and keep intact Maxwell's equations. So the laws of mechanics, that is Newton's laws, had to be modified and to hold for velocities far lower than the speed of light. So that's the relativistic momentum, and that's the relativistic formulation of Newton's law with this gamma, which involves the Lorentz transformation, as I noted above. So this was the situation at the beginning of the 20th century, 1905, 1910. And this meant that an important philosophical system that was in place back then, the system of Immanuel Kant, had to actually be reworked, be revised, be reshaped. Now, Kant is very famous for believing that there are synthetic a priori principles, that is, principles which are independent of experience, that is, sorry, and therefore necessary and therefore immune to revision, which, however, tell us something about the structure of the world. They've got synthetic content, as it were, and these principles are necessary and are revisable and are required for the very possibility of experience and of science. That's the only famous person that ever became a stamp. That's Moritz Schlick. Moritz Schlick is the founder of the Vienna Circle, a famous philosopher of science and one of the philosophical innovators in the 20th century. So Einstein wrote to Schlick. They had an exchange about relativity theory. He wrote to Schlick in 1915, "Truly masterful is your position to the doctrine of Kant," referring to the doctrine of Schlick's. "The trust in the apodictic certainty of synthetic a priori judgments is already undermined heavily if one realizes the invalidity of even just one of these judgments." So Kant was wrong, and Einstein was very keen to make this point. But this actually made the following issue very prominent. What is the status of the basic principles of science? And concomitantly, what is the right method for doing science? So Einstein actually endorsed the atomic theory of matter, and at the same time he endorsed the special and general theories of relativity. But these are different theories. The atomic theory of matter posits these little things, the molecules, the atoms. No one has ever seen an atom, no one has ever seen a molecule by naked eye, but nonetheless, by hypothesizing these little things, it explains all macroscopic phenomena on the basis of the properties and the laws of the interactions of atoms. On the other hand, the special theory of relativity does not seem to rely on big hypotheses, at least hypotheses of this sort. It relies, as Chris explained last week, on two major principles. The principle of relativity, all frameworks which are connected by Lorentz transformation are inertial frameworks and all laws of nature hold in them, and the light postulate, the postulate that the light has a constant velocity independently of the state of motion of the source and of the observer. Now, what do these principles do? They impose general constraints on the spatio-temporal structure of the world and the laws of motion. So one could say that the atomic theory of matter relies on hypotheses, and the spatial relativity relies on principles. Is there a difference in these two types of theory? Now, within the space of 1 month, roughly, Einstein wrote two important philosophical pieces in 1919. November 28th in the Times, London Times, What is the Theory of Relativity? And then we'll see it in a while in a German magazine in Christmas of 1919 about the method of science. So in this particular piece, where he explains to the general public what the relativity is about, he makes a very interesting distinction between two types of theory, what he called constructive theories and what he calls principle theories. So constructive theories, as he says, are attempts to build up a picture of the more complex phenomena out of the materials of a relatively simple formal scheme for which they stand out. So the example here, to make it clear, is the kinetic theory of gases, the atomic theory of matter, in other words, which seeks to reduce mechanical, thermal, and diffusional processes to movements of molecules, i.e. to build them up out of the hypothesis of molecular motion. You start with these little things, you don't see them, you hypothesize the laws they obey, and somehow you manage to explain everything that you see, you observe, you experiment with on the basis of these little things and the laws they obey. The principle theories, on the other hand, he says, the elements which form the basis and starting point, the principles, are not hypothetically constructed but empirically discovered principles, general characteristics of natural processes, principles that give rise to mathematically formulated criteria which the separate processes or the theoretical representations of them have to satisfy. The example here is what is called phenomenological thermodynamics, before statistical mechanics, before the atomic theory of matter, where basically, as he says, seeks by analytical means to deduce necessary conditions which separate events have to satisfy from the universally experienced fact that perpetual motion is impossible. So the idea here is that you start with a principle which is empirically grounded, that there is no perpetual motion, and you use this principle to explain various other laws, the laws of the gases, etc., etc. So there are two different types of theory, and Einstein toys with the idea that there is an epistemological difference between them. He says constructive theories are explanatory, they rely on hypotheses. Principle theories avoid hypotheses, start with general principles and try to explain everything on this basis. And he says there is prima facie a difference, actually prima facie is mine. He says there is a difference between them. Constructive speculation, if you hypothesize little things unseen by the naked eye, increases the distance between the foundation of a theory and sense experience. So a theory which posits all these little things to be seen, like molecules and atoms, is more risky theory because it's far away from what we ordinarily experience by means of observation and experiments. So it seems as though principle theories seem to stay closer to experience and therefore be more certain than hypothetical constructive theories. However, for Einstein, that's not reason for skepticism. Even if that's so, speculative theories can achieve, he said, logical unity and can unify various seemingly disparate phenomena. Not just that. He talked about the kinetic theory of gases, that's in the 1919 paper in the Times. He said what made the turning point for the acceptance of this theory was that it produced definite values for the true magnitudes or atoms and molecules, which resulted from several independent methods and were thus placed beyond the realm of reasonable doubt. The highlighted words are really important: definite values and independent methods. Here there is an allusion to the work made by Jean Perrin, who actually showed that there are 13 different ways or so to calculate Avogadro's number. Avogadro's number is a number hypothesized, and it's got to do with the number of molecules in a certain volume of a gas. This got to be a certain number, 6.023 to the power of 23, but nonetheless, we've got a definite value of the properties of atoms and a definite and multiple ways actually to calculate this number. So Einstein says the constructively speculative character of some entities is not a reason to doubt their existence. That's a beautiful quote. Nobody could ever hope to perceive directly an atom, Einstein says. Still, we shouldn't doubt their existence because laws concerning variables connected more directly with experimental facts, for example, temperature, pressure, speed, were deduced from the fundamental ideas hypothesis by means of complicated calculations. So Einstein seems to say, and I think that's a good point, successful and rigorous testing of a theory together with the unification of various seemingly disparate phenomena by the theory are sufficient for accepting the reality of the entities posited by the theory. So he was never a skeptic about electrons and other elements of the microstructure. Actually, he was very critical of Newton. Because he took Newton to be an advocate of inductivism, and he said, we now realize with special clarity how much in error are those theorists who believe that the theory comes inductively from experience. Even the great Newton could not free himself from this error, and he refers to hypothesis non fingo. So he was very clear that you cannot get to the fundamental principles by means of experience. They've got to be hypotheses of some sort. Now, the other piece I was talking about was published a few weeks after the piece in the London Times. It's called Induction and Deduction in Physics in Berliner Tageblatt. And there he makes an interesting distinction between induction on the one hand. He says individual facts are selected and grouped together such that their lawful connection becomes clearly apparent. By grouping these laws together, one can achieve other more general laws until a more or less uniform system for the available individual facts has been established. So you start from the bottom and you go up by individual facts, which you generalize and generalize until you reach some general principles which apply to all the facts you've examined. But he immediately notes that this is hopeless. You cannot get to the fundamental principles like that. So he contrasts that. He didn't use the expression hypothetical deduction, which is more modern terminology. He talked about the intuitive method. But of course, we should be very careful because Jean Perrin himself, the French physicist, when he was actually defending his own method, the hypothesis of atoms and the explanation of everything on its basis, he took this method intuitive deductive. So it's mostly a way to dissociate it from induction, from a direct generalization from experience to call it intuitive, not that you intuit the essences or the natures of these entities. And he says the intuitive grasp of the essentials or a large complex of facts leads the scientist to the postulation of a hypothetical basic law or several such laws. From this basic law, he derives his conclusion as completely as possible in a purely logically deductive manner. These conclusions derived from the basic laws can then be compared to experience and in this manner provide criteria for the justification of the assumed basic law. So what he says is that we don't do it bottom up, we do it top down. We start with postulates, with hypotheses, we deduce observations, empirical laws and predictions, we test them experimentally, and if they are borne out, then we kind of trust or believe in the truth of these hypotheses. That's the intuitive method, which he thinks it's a method of science as opposed to the inductive method, bottom-up generalizations. But is there a conflict in the two positions? Within a space of 1 month, Einstein seems to be saying that principal theories are not hypothetical and they don't involve hypotheses, whereas the constructive theories are hypothetical, and therefore somehow we should avoid principal theories, as it were, because the method of science should be we start with hypotheses and we derive from them predictions by means of deduction. I don't think there is a real tension here because the principles of the principal theories go beyond experience. They generalize a lot beyond what we've actually seen. And of course, they are hypothetical. They hypothesize that what we've observed as holding in particular cases hold generally equally well. But I think that's an important insight Einstein had, that they're hypothetical in a different sense than the hypothesis of the constructive theories. So it's two kinds of principles, and I think two kinds of hypotheses. I call them speculative or vertical, and comprehensive or horizontal. I'm not tied to these expressions. I think they can be improved upon, but I think the idea here is that with a speculative theory, we dig vertically. We try to find the microstructure by means of which we try to ground the behavior of observable things and laws, whereas with the principle theories, the principal hypothesis, let's put them, we go horizontally. We extend what we've seen as holding in various good cases to general principles. Now, both are needed for science, both promote unity, both are testable. More importantly, for Einstein, both are creations of the human mind. And that's an important message he wants to send. Science is not a passive taking in of facts of experience, which are generalized by induction. There is an ineliminable active element in science, a contribution of the human mind, which comes across when we think of the hypothesis as being freely created and adopted by the human mind and being tested deductively by means of predictions. So although Einstein was in disagreement with Kant about synthetic a priori principles and with Poincaré about conventions, he accepted an extremely important aspect of Kant's philosophy. Kant says experience is receptive, experience receives things, but the understanding is active. It's spontaneous, the spontaneity of the understanding, that somehow the understanding has to produce the categories or the general concepts by means of which we view and try to understand the world is a key element of Kant's thought, and I think Einstein was actually in agreement with that, and that's the way he understood this idea of the free creation of the human mind. Now, to see a little bit more about this distinction, in 1918, the 60th birthday of a great physicist, Max Planck, Einstein again gave a talk. He talked again about intuition, which leads to principles, and he insisted there is no logic of discovery. There is no algorithmic path from what we experience to some principles by means of which we try to understand the world. There is no logical path to these laws. Only intuition resting on sympathetic understanding of experience can reach them. And many, many years later, to see that that's a constant part of his thought, that's 1933, the Herbert Spencer lecture in physics, a famous lecture titled On the Method of Physics. I'm going to read it out, it's beautiful. The structure of the system is the work of reason, the system of science, the theoretical system. The empirical contents and their mutual relations must find their representation in the conclusions of the theory, in what the conclusion says about, the theory says about the world. In the possibility of such a representation lie the sole value and justification of the whole system, and especially of the concepts and fundamental principles which underlie it. Do you get experience right by means of that? That's where, and do you get the structure of the world right by doing that? That's the sole value and justification of the whole system. Apart from that, this latter, that is the concepts and principles, are free inventions of the human intellect, which cannot be justified either by the nature of the intellect or in any other fashion a priori. These fundamental concepts and postulates, which cannot be further reduced logically, form the essential part of a theory which reason cannot touch. It is the grand object of all theory to make these irreducible elements as simple and as few in number as possible without having to renounce the adequate representation of any empirical content whatever. So Einstein again says there are two constraints in how we do science. We need to get the facts right. We need to get the predictions, the empirical laws right. But we have to do that by a unified system of the world, by a system, a theoretical system, which uses as few principles as possible. Why does he say that? Einstein, as a good Aristotelian, I guess, as a good philosopher, he was thinking that all explanation requires unexplained explainers. Explanation cannot go back forever. You've got to assume something as a starting point and try to explain everything on its basis. But the fewer the unexplained explainers are, the fewer the assumptions you make as primitive, the more your understanding of the world is, the fewer things you take as unexplained themselves. You take them as unexplained, but you manage to explain as many things as possible. So unification for Einstein is an important element of scientific theorizing. It's an indispensable element. It's actually an element which somehow is a mark of truth, or of getting closer to the truth, as it were, of scientific theories. So it's really important to think of his anti-inductivism as something that actually grew stronger and stronger as time went by. And as he himself says, it was basically the path to the general theory of relativity, which Chris spoke about last week, which made him a kind of a convinced anti-inductivist about theories. There was no way simply in which the theory of relativity could be formulated as a generalization from experience. For instance, the generalization of relativity principle to all frames of reference, be they inertial or accelerated frames of reference, is not an inductive leap. He actually spoke about principles like symmetry and simplicity, which led him to make the generalization of the relativity principles to all frames, be they accelerated or inertial. From the theoretical point of view, this theory is not wholly satisfactory, the special theory of relativity and the early versions of the general theory, because the principle of relativity just formulated favors uniform motion. It is true that no absolute significance must be attached to uniform motion from the physical point of view. If it is true that no absolute significance must be attached to uniform motion from the physical point of view, the question arises whether this statement must not also be extended to non-uniform motion. So that's not an inductive leap. He says, look, I see no physical reason why we should make uniform motion, that is rectilinear motion with constant velocity, inertial motion, privileged. Why we should put it in a box separately from all other kinds of motion, namely accelerated motion. So there's no induction here. There is a generalization, if you like, on the basis of principles of symmetry and simplicity. And that's a beautiful quotation also, which I want to read out, because it shows his anti-inductivism, a clear recognition of the erroneousness of the idea that the postulates of physics are not in the logical sense free inventions of the human mind. That is a clear recognition of the erroneousness of inductivism, really only came with the general theory of relativity, which showed that one could take account of the wider range of empirical facts, and that too in a more satisfactory and complete manner on a foundation quite different from the Newtonian. So what Einstein says here is this: we've got a beautiful theory, Newton's theory. It explained more or less everything. It had a few little things that needed to explain, but in the end we had to revise the theory radically and to devise a new theory, general theory of relativity about gravity and the structure of space, to account for the phenomena in a more satisfactory and more complete manner. And that's not an inductive path, that's a path which is creative. The human mind, somehow the scientist's mind, creates hypotheses and principles by means of which it understands and explains the world. Now there is a question here, and it's an important philosophical question that bothered Einstein very much. And these are quotations to show that I don't make it up. And that's a great way to put it, actually. He says, if then it is true that the axiomatic basis of theoretical physics cannot be extracted from experience, but must be freely invented, can we ever hope to find the right way? Why are we free creations anything to do with the world, with reality? Nay, more has this right way any existence outside our illusions. Can we hope to be guided safely by experience at all when there exist theories which to a large extent do justice to experience without getting to the root of the matter? He says, how can we make the connection between our theories we devise, which are not derived from experience, to the world? How can we say that they're not whimsical, idiosyncratic construction of the human mind, illusions? How do they somehow latch onto the world? And he says, I answer without hesitation that there is, in my opinion, a right way, that is somehow the theory latches onto the world in a right way, and that we are capable of finding it. So it's not that there is just one way, but he was an epistemological optimist, that we can find what this way is. We can find out the truth, if you like, or the right way to connect our theories to the world. But his views were a little bit strange, because he said, our experience hitherto justifies us in believing that nature is the realization of the simplest conceivable mathematical ideas. So nature is mathematical in itself, and somehow we can, he says, I'm convinced that we can discover by means of purely mathematical constructions the concepts and the laws connecting them with each other, which furnish the key to the understanding of natural phenomena. Experience may suggest the appropriate mathematical concepts, but they most certainly cannot be deduced from it. Experience remains, of course, the sole criterion of the physical utility of a mathematical construction. So the difference here for Einstein is that the human mind, the scientist's mind, by being able to use mathematics somehow can be able to construct all these beautiful mathematical theories in mathematical physics and try to apply them to the world, test them directly by means of experience. But somehow this whole process works because the structure of the world somehow has mathematics into it. The mathematics somehow latches onto the world by being the realization, by nature being the realization of the simplest conceivable mathematical ideas. So you need them both, actually. You need both the mathematical ingenuity with the Einstein's equations of gravity, and you need something like Eddington's experiment of the bending of the light rays to confirm the theory. But you need them both to have a matching between the theory and the world. So I'm drawing to a close, and now we're going forward to 1952. Einstein had a lifelong friend, Solovin. I don't quite recall his first name, but he was in extended correspondence with him. And that's a beautiful stamp, and that's a beautiful sketch of something that he actually wrote to Solovin. And he says something like that. That's another long quotation, but it's very interesting. The solid line is experience. Okay? A are the axioms of the theory. From the axioms of the theory, you derive various lesser axioms or statements, S, S prime, S double prime. And then you see this kind of funny arrow, which, not a straight arrow, which leads from experience somehow to the axioms. Okay? And he says, the E's are our data, what we get in experience. The axioms from which we draw our conclusions are indicated by A in this graph. Psychologically, the A depends on the E's, on what we learn from experience, but he says there is no logical route leading from the E's to the A's, but only an intuitive connection, which is always returning. That is, there is no empirical path which leads you directly from experience to the axioms. The axioms are what he said, the basic principles of the hypothesis, the free creations of the scientists. Then from these axioms you derive logically specific statements, and these statements can lay claim to exactness. So, but then he adds a new layer of significance, because he says the A's are connected to the E's, to what we learn from experience or inexperience, but closer examination, how the theory actually connects to experience, to how the world is given to us by means of our senses roughly, shows that this procedure also belongs to the extra-logical intuitive sphere for the relation between the notions show up in S and the immediate experiences are not logical in nature. So he says there is some creativity also involved in moving from what we experience directly from the senses to the empirical laws, the S's, the statements which the theory saves by deducing them from the basic axioms. But the relation between S's and E's is pragmatically much less certain than the relation between the A's and the A's. Take the notion dog and the corresponding immediate experiences. If such a relationship could not be set up with a high degree of certainty, logical machinery would have no value in the comprehension of reality. So it's not only that there is creativity in the way in which the principles are devised vis-a-vis the various experimental laws, there is creativity in the way we go from immediate experiences, sense data if you like, or whatever is given to us directly by means of the senses, to the empirical structures which the theory should save by means of deductive entailments. Now compare these two graphs now. I think Aristotle never drew this, of course, okay? But it's something you can extract out of a famous chapter in posterior analytics, the B19, and Aristotle never got the chance to be the person of the year or the century or the person of the millennium, but they were actually groping with the same conceptual philosophical problem. And that's a key thing in understanding how scientists can engage in philosophical activity. And the philosophical problem is precisely how these things connect to each other, how experience leads is connected to the principles by means of which we try to understand the world, how then the principles by means of which we understand the world yield further empirical laws and how these are basically tested. Now, for Aristotle, that's induction, but it's most like a placeholder for whatever process is there, by means of which the mind, starting from experience, goes to the principles. Although for Aristotle, induction should start from experience from particular things, Einstein insists that this cannot be induction, although somehow it must start from experience. There is no other way to start if you do science. The philosophical problem is not solved, but philosophical problems are not meant to be solved. The philosophical problems are kind of eternal problems. We try somehow to understand the complexity of the problems and make some progress in thinking about possible solutions or ways to address them. What's important, and I'm going to finish with that, is that Einstein offered a solution to Aristotle's philosophical problem in an attempt to understand how the new scientific worldview had come about. This is engaging philosophy at its best. Philosophy is simply not optional for the scientist that aims to engage in the critical contemplation of the theoretical foundations of science. Thank you very much. Questions? Is it going to be questions or the J's? The gentleman in the back.
The basic problem of observation. For example, two people looking at the same event, seeing two different things.
You think that's true?
Yes.
And you think that's true also perceptually? They perceive the same, the content of their experience is different, or how they interpret their experiences?
Two people witnessing the same traffic accident.
Mm-hmm. It's interesting because there's some debate about what is happening in this case. You know, there are two schools. I'm not sure how Einstein would answer this question. I'm not here to say this, but the claim is that some philosophers and psychologists think that there is a level of description of the perceptual content which is independent of our concepts and theories. So in a sense, we see exactly the same thing if we stand in the same angle when we watch a traffic accident. Okay. But however, experience is not just perception, it's not just the perceptual content of experience, it's how we embed that in concepts. So there is conceptual content in experience. And if it's conceptual content, then we might have different interpretations. So you saw an accident happening because the driver, was a little bit tipsy, you think, or it was you saw an accident because, something else happened. So it's not an easy answer to it depends very much on how you think. You take in facts by means of experience and what school of thought you associate with. Yes?
What type of experience was Einstein drawing off of before he made his conclusions?
It's basically various laws, the laws of the kinetic theory of gases, for instance. These are not kind of experience in the sense of given to us directly by the senses, because there are already some empirical generalizations. So the law of the gases says that there is a functional relationship between pressure, volume, and temperature of a gas. Now, this is already generalization. That's something that you get by plotting various values on a graph and finding, even by theoretical means, the simplest curve that connects these dots that you actually think represent points of measurement. So it's already beyond experience, immediate experience in the sense of sense experience, because you've moved to, by using statistical principles and other methods, you use to kind of low-level empirical generalizations, which the theory tries to account. So what you were saying there was that you've got a dual problem. How you connect the theory to these generalizations, and how you connect the generalizations to the content of your experience in the strict sense of what is given to you by the senses.
But I don't know which variables to take out of your experience and to make that theory.
This is theory given. Presumably you find some connection empirically between, the volume of the gas and the pressure. And you think that these are causally relevant magnitudes, and you try to find some lawful connection between them.
does it depend on if you actually want to use it for something, or is it just a phenomenon in of itself?
It could be both, I think. It could be because you made some observations and experiments which led you to this, and you try to explain how this happened in a kind of a curious way, or because you somehow you want to probe nature by asking a certain question. So an interesting thing is that take the speed of light. The speed of light was very well known that it's a constant speed by the Danish physicist something Ørsted, I don't quite recall his first name, and it was a kind of an empirical observation having to do with how that light takes time to reach us when he observed the satellites of Jupiter. But then from this move to the claim that the speed or the velocity of the electromagnetic waves is the same as the speed of light, that's a theoretical generalization. That's something that takes you beyond experience because you identify two different processes.
Also, the media is different too.
Yeah. Yes.
Aristotle was a pretty smart guy, and but in his day, there probably weren't any sort of verified events that contradicted perception. I'm thinking. Does that sound right to you? You know, like this, light not being additive with the.
Yeah. It sounds right to me to some extent. There were issues there were skeptical challenges, but they were kind of local skeptical challenges. So everybody knew back then, as they know now, that where you put a stick in a glass of water, it appears broken, though it's not. So things might appear differently than they actually are, but you can always use the other senses or other ways to identify what is going on in this case. So that's why, although there were kind of global skeptical positions in ancient Greek philosophy like Sextus Empiricus and others, they never became universally accepted, or they never set the standards of knowledge. But from the 17th century on, things changed quite dramatically, because now you know, if you're a serious scientist after 1543, that you've got two ways to view the world which are indistinguishable, namely the Copernican and the Ptolemaic, the geocentric and the heliocentric. Therefore, somehow appearances might be totally different from reality. How things are might be totally different from how things appear to you. Therefore, there's a new challenge, which is to go beyond the appearances and find out what the reality is. And on top of that, if I may say so, because I like to say that whenever I talk, the other constraint about this move from appearances to reality is that reality should be understood as having a microstructure, and the microstructure being responsible for the macrostructure of the behavior. So what you get from the 17th century on is a dual conceptual shift. Reality is different from appearances, and the reality which is different from appearances is a microstructure, mechanical philosophy, matter in motion, and the aim of science is to tell this story, to find out the reality behind the appearances, and at the same time describe the reality with these microstructural components in place. Am I answering the question? The gentleman over here, and then the gentleman. Yeah.
I'd like to take what the first man said and take it one step farther about two people seeing the same thing and seeing it differently. I had a friend who couldn't wear a watch because they would stop. Every watch he put on stopped. So I can wear my watch and it works. He can wear my watch and it doesn't work. So we, the two of us, make different realities. So if we expand that concept, then whoever puts out the theory makes the universe that way.
I would be, following Einstein, I would be very cautious in generalizing from this particular case to how we should behave, how we should think generally. Generally, I think we should be very careful. I mean, I'm not talking about what you said, but generally, a lot of philosophers take very easily the thought that somehow we make up reality, we construct reality. Theories and conceptual frameworks make reality what it is. Now, notice that Einstein was very, he was opposing this idea quite severely. He thought there is a right way to describe reality and somehow tell a story as to how we manage to find the right way. But there are problems with the view. Let's say the neo-idealist view that somehow theories or paradigms construct reality. And the problem is precisely what led Einstein's theory to become widely acceptable. Chris spoke about that last week. The Eddington experiment. The Eddington experiment, or the anomalous perihelion of Mercury, that's even more important in a sense. Because Mercury makes a very anomalous trajectory. Somehow when it's at the perihelion is the furthest away from the sun, is it not? Then if you look at it, over time, it seems as though it makes a kind of a very anomalous trajectory which does not look like an ellipse. That's a huge anomaly for Newton's theory. And everybody knew that, and everybody was expecting that somehow this anomaly should be corrected. And very serious people thought there is a new planet over there called Vulcan, which somehow is mass enough to disturb the motion of Mercury so that this anomalous perihelion is explained. No one observed Vulcan, and the anomaly was so severe that it was Einstein's theory that solved it. And as Chris said last week, he was joyful when he found out that he could actually calculate the 43, for God's sake, the 43 minutes or whatever it is of an arc, which is nothing. But per century, okay, which is nothing if you think of it. He was joyful, and Hilbert said you calculate faster than the speed of light, something like that. So the idea is this: you've got anomalies, and if you've got anomalies which are persistent and diachronic, you cannot really construct the world. Because if you were to construct the world, why would there be anomalies? Why something you construct has an anomalous structure? Why something you constitute by your concept and theory such that it resists being incorporated in your theories? So I think these views are far too extreme, for me at least, to adopt.
With respect to the question at the back,
Yeah.
during Einstein's time, say before quantum mechanics, kinetic theory was totally Newtonian. So you shouldn't use Newtonian theory since it agrees with experiment at that time completely, it shouldn't be used to justify anything that Newton says against Newtonian theory. Kinetic theory in 1905 was completely Newtonian. Brownian motion is
Everything was completely Newtonian back in 1905, and then
yes.
Einstein thought that it shouldn't be,
Yes.
because we should keep Maxwell's equations and change Newton's laws.
Yes,
But on the other hand, you see, that's a very important point. If I can interpret your question in one way, you see, Einstein would strive to show that he could derive Newton's laws as limiting cases from his own theory. And both in the special theory and the general theory, Newton's laws of gravity. So they act as constraints on theorizing, so you don't throw the whole theory away because it's changed. You try to keep it as a limiting case and show why it is applicable to the extent that it is applicable in the world. And there are very many complicated issues here about whether it's approximately true and to what extent it is approximately true, but it's too late even to contemplate on them. Other questions? Yes, sir.
Okay, I'm just wondering, a famous name when it comes to the philosophy of science would be Karl Popper.
Yeah.
And I'm just wondering, where does Einstein stand in relation to Karl Popper?
Yes. Now, I hate to say that Einstein was closer to Popper than I would have expected him to be. So there is some correspondence between Popper and Einstein. And Einstein seems to be saying to Popper something like, you are right in stressing falsification. So the theories, you test a theory by exposing it to falsifying instances and trying to refute it. And Einstein was very sympathetic to this idea. And I don't think there is anything wrong with this idea, but it's just an incomplete idea. You cannot do science by just trying to falsify theories, but trying to refute them. precisely because at any given point you want to say that the unrefuted theory, the theory that has not been refuted by the evidence so far, has a chance to be correctly described in the world. And the Popperian account never issues judgments like that. The Popperian account never issues judgments of probability or likelihood of theories. All you go for is trying to falsify a theory and throw it in the litter bin if actually is falsified and go for a new one.
Right.
But Einstein was very sympathetic to this idea.
Okay, because so I'm wondering because I believe he said that Einstein believed that the truth can be found.
Yeah.
Popper, I believe, said that the sun can rise today, can rise tomorrow, the next day, 1,000 days, but you don't know it's going to rise. You still don't know if it's going to rise tomorrow. And you can never be certain.
No, that's absolutely right. We actually, not only can we never be certain, but induction as a way to reach a conclusion that it will likely arise tomorrow is bankrupt. It's a way, it's a psychological illusion. We don't perform induction, we think we do. Popper was interesting precisely because he was against truth when it comes to whether you accept a theory as being true, but he had, especially in the later part of his life, he had this idea of verisimilitude. It's a strange idea, verisimilitude, similarity to truth. So I think he coined the term verisimilitude, which is a strange English word. And he wanted to show that somehow as theories grow and theories change, you somehow go to truer theories of the world. You may never be able to reach the truth, whatever that is, but you go from a truer to more truer description, to a truth, to a partly true, from a partly true to a more true or truer description of the world. But this was a kind of a magical addition. It was never justified by the epistemology that Popper wanted to put in place, I think. Yes?
Why is it called a theory of relativity rather than fact?
That's a very interesting question because I think, the term theory is a very interesting term itself, and you've got to see it in a complex network of concepts like model, hypothesis, theory, and it seems to me, and that's a guess, that it's partly grounded in historical studies at the end of the 19th century, that theory was always an honorific term to some hypotheses or models who were widely accepted and considered as true. So to call it a theory was already something beyond hypothesis, beyond the model. So it was something to single it out from other things which were more speculative, if you like, or less certain than the theory. But we now believe that relativity is a fact, although the principle of relativity describes a fact about the world. There's no tension there. Why do we call it a theory? In a sense, that's a sociological question anymore. I think it's kind of how scientists decide to use the concepts.
What's the utility value of this theory, say, compared to actual fact-based data?
I don't think that we can speak in terms of utility. I think, special and general theory of relativity describe deep symmetries and facts about the spatio-temporal structure and the gravitational structure of the world. There are serious problems nowadays because it's not easy to reconcile quantum mechanics with relativity, and I think next week Doreen will talk about this issue and Einstein's reservations about quantum mechanics precisely on these grounds. But it's not so useful now to go into details about that, I think. The lady in the back.
When you're talking about the intuitive method,
Yeah.
how would Einstein have defined the sympathetic understanding?
Open-minded understanding in terms of, I think, trying to find out the causes or the general principles by means of which things work in the world. because there is always the option or the possibility that you are skeptical about science, that is, that you say that we're kind of closed within the veil of appearances or the veil of perception. We can never go behind it, we can never find out what the structure of reality is behind how things appear to us. So a sympathetic understanding is what I have called, in other words, open-mindedness, epistemological open-mindedness, that somehow we can come to find out when a hypothesis is likely to be true.
And would you have taken that in his definition, would you have taken that further than the five senses, like the finite senses? He's gone further because that open mind is very defined.
To me, the idea of intuition is a bit unclear, as I said. It's mostly to do, it's not as if there is an extra faculty. I don't think he meant we got an extra faculty. There are the six senses and there is an extra faculty by means of which we intuit principles. And there is no evidence that he believed in something like that. Other scientists and philosophers believe in something like an extra faculty. Gödel, the famous mathematician, believed that there is an intuition, something like a faculty we've got to understand mathematical truths. So he mostly wanted to say that the human mind, the scientific mind, can devise hypotheses, can theorize freely and try to test these theories empirically and unifying them. So unity and empirical testing are the two ways to test, to accept the hypothesis as being true, although it's a free creation. It's not forced on you by experience. Yes?
How did Einstein feel about, like, you talked about he worked towards a logically consistent theory. How do you feel about the discrepancy between the theory of relativity and quantum mechanics that he...
No, that's, I mean, it bugged him a lot. I mean, that's something that he was feeling extremely uncomfortable about, and I think he never accepted, he never took quantum mechanics seriously because he always thought it's an incomplete description of reality, and there was a tension between relativistic formulations and non-relativistic formulations. But I'm not prepared to discuss in any detail what he felt. I mean, I know a fair amount about his views on quantum mechanics, but he was always driven by the requirement of unity because he deeply thought that there must be some single unified description of the world which somehow sorts everything out. And I think what attracted him to electromagnetism was precisely that Maxwell's theory provided this new framework by means of which you view the world ultimately as electromagnetical, and all processes are ultimately being electromagnetical, and then mechanical processes even being reduced to electromagnetism as opposed to the other way around.
Thank you.
You're welcome. I think there are no more questions. So time for the Blue Jays if the result is not out yet. Thank you so much.